Hi, my name is Yeong Park. Actually, I'm the co-first author of this paper, and I'm from the University of Minnesota, which I recently graduated from. And this research is done with collaboration with Jungkook Park and Professor Elisa Oh at UIST. So I'm going to talk about the nonlinear editing techniques for the text-based screencasts. So if you have ever tried learning some new programming skills recently, you might have watched some YouTube videos that look like this. So these are the screencasts where the person records their screen while they are writing some code and explaining something to the audience. So this particular format is getting increasingly popular on the internet, especially for the programming tutorials. And since these videos are essentially the recordings of text edits, the actual content can be represented in text changes. So instead of recording the screencast in a video format, some people figured they could record text operations instead, and make it seem like a video. And so why would you need this new format? Why don't we just use the video format? To give you some idea about the benefits of using this new format, let me show you a text-based screencast here. So this is a random screencast I found from Screenba, which is a website that hosts text-based screencasts. And if I play this video, as you can see, the user can watch the screencast like the video. But then the user can pause the screencast and edit the content in the screencast, or even run the code. So being able to preserve the text in the screencast makes it possible for the users to interact with the text within the screencast. However, one of the challenges that for the text-based screencast is that there's no editing tools available for the creators to edit the screencast after recording. This makes it very difficult for the creators to create high-quality contents. So we set out to solve this problem, and it turns out that editing a text-based screencast is not an easy task. The fundamental issue here is that the text operations in sequence has a causal structure. So if you make some changes to the screencast, there might be multiple possible outcomes that you get from the edit. So we need some kind of resolution strategy to get a single edited version for the screencast, just like a time machine paradox. So to illustrate this problem, let's imagine we have a user who created a screencast represented on the left. The user was trying to record a screencast typing the quick brown fox. But then she realizes that she made a typo while she was writing the brown. So she goes back in time and she inserts a new operation of inserting the letter O. Now, here's the problem. Since the insertion of the letter W in the original screencast has the same position with the new insertion of the letter O, there's an ambiguity. So there are three different possibilities for this transformation for this next frame of the screencast. But how do we know which one is the one that user intended? It turns out that the system cannot automatically choose the right one for the user because it doesn't understand the semantics of the content. This is synonymous to the semantic consistency problem in collaborative editing research. Or if you're familiar with the version control systems, this is somewhat similar to the merge conflict resolution. So our approach is to let the user make their decision. Pretty straightforward. So in this case, the user will choose the one in the middle. And we have the screencast has converged to the one version. So let me show you how this actually works in our prototype. So the user can record a screencast and go back and find the point to edit, resolve the ambiguity, and we have the screencast, edited screencast. So here is the overview of our contributions. First, we present the nonlinear editing algorithm for the text-based screencasts. And then we have created a prototype editor that implements the nonlinear editing functionality for the text-based screencasts. We also did an exploratory user study to demonstrate that users can successfully edit a text-based screencast using our editor. So first, I'm going to talk about the algorithm. So initially, the algorithm is given the original screencast, which is represented in this blue block. And we are also given the time range to be replaced and the new screencast segment that will replace the time range. So we remove the part that is supposed to be removed, and then we append the new segment to the screencast. And now we have to bring back the letter part that we took out from the screencast. However, we can't just append the letter part to the new screencast because it has a different historical context. So in other words, the letter part is based on the original screencast that is no longer there. So we have to transform the letter part before we can append it to the screencast. And also, if there's an ambiguity occurring from this edit, we also have to ask the user to resolve the ambiguity during the transformation. So this is the core of this algorithm. So how do we detect the ambiguities? And if there's an ambiguity, how do we calculate all the possible transformation for the resolution of that ambiguity? The first step is to mark what we call the ambiguous area in the original version of the screencast. The ambiguous area represents the positions that are affected by the new operations. So in this case, since the letter X and Y are inserted on the right next to the letter A, we mark the position as ambiguous area that corresponds to the XY. Then the next step is to check whether the next operation from the original screencast timeline overlaps with the ambiguous area. So in this particular case, the letter B is inserted next to the A, so that overlaps with the ambiguous area that we marked before. Therefore, there will be an ambiguity. And finally, we calculate all the possible transformation by putting together the operations from the original screencast and the new operations from the edit. We get all the different combinations for these two operations and let the user choose one of the possibilities so it converts to the one single screencast. So the user chooses one and it converges. And now let's say there was another operation in the original screencast. Then we now repeat the same procedure like before. Again, we have two ambiguous areas this time. And each corresponds to the letter X and Y in the original version, respectively. And because the insertion of the CD overlaps with the second ambiguous area, we get yet another ambiguity. So we calculate the transformations by getting the different combinations of the letter Y and the C and D. And we repeat this process until all the text operations in the letter part are transformed. The OT stands for operational transformation. We use internally for our representation for text edits. So now we are moving on to the interface. This is the screencast of our prototype interface. So you can record the text-based screencast, and of course you can edit the screencast. So the first thing you have to do in order to edit the screencast is to select the time range that you want to replace, and click the button to start the recording. When you finish the recording, and if there's any ambiguity occurring from the edit, this window shows up. The ambiguity is over. So here you can see what's going on with the ambiguity, and you can choose the resolution that you want. So it basically works like a three-way merge system. So on the top, you have the before and after in the original screencast timeline. And at the bottom, you have two text areas that shows you the before and after within the edited timeline. And if you look at the bottom left corner carefully, there's a two from and to handles that you can move around to select the right transformation that you want for this particular ambiguity. So that was the interface. So let's talk about the user study. So through the user study, we wanted to see if the users could successfully perform the edit in any editing scenarios. And we also wanted to see how easily the users could learn the ambiguity resolution process and how fast they can get used to it. So we recruited 6 participants. Most of them had some experience in creating screencasts before in video format. So we gave them tutorials for the tool for 10 minutes. And then we let them record the 10-minute screencast and perform 4 different editing tasks, followed by a semi-structured interview for 15 minutes. So the 4 tasks, the first one is to record the screencast. So the remaining, the last 4 tasks are the editing tasks. So when we are designing the tasks, we try to make the tasks as much as possible to reflect the real-world editing use cases. And we also wanted to make sure the editing happens, editing is distributed evenly throughout the screencast. And then I'll just give you some highlights for the result. So as a result, all of our participants completed successfully the given tasks. And we look at the numbers. About half of the edits caused ambiguity, and each ambiguity required about 1.45 decisions. And people spent about 19 seconds to resolve an ambiguity. Although it was pretty successful, people said the ambiguity resolution process was quite difficult. So the most interesting thing is that the people said they were confused because they couldn't remember the screencast exactly, even though they just finished recording the screencast. Because they don't remember the operations that they recorded, they just don't know how they could, what they are dealing with. And even if you remember the content all the way through the end of the screencast, it's fairly difficult to know how this edit will affect the later part, how this will cause which ambiguity. And the problem is exaggerated by the fact that we only show the next frame, although the operations are very fine-grained. So we need to design something to give the users more context, to give sense of what they are doing. Also, in overall, many subjects said the ambiguity resolution process is just too complicated to handle. So they just tried to avoid creating any ambiguity, or just randomly chose the transformation. So for the future research directions, we definitely need to improve the interface design for the ambiguity resolution. And we also have to consider how we can make the ambiguity resolution less difficult by limiting the number of possibilities in the beginning. So we open sourced our implementation for the algorithm and the interface. So you can go check it out on GitHub. And we didn't prepare the demo yesterday, so if you're interested in the demo, you can just find one of us and just ask for the demo, probably. So that's the end of the presentation. Thank you.
So do we have any questions? Go ahead, Takeo.
Hi, I'm Takeo from Tokyo. So you're working on code, right, basically?
Yeah, it could be anything that's based on text. We are mostly focusing on the code because most of the videos we found on the internet is programming tutorials, but it can be any content that has text on it.
So with this code, is it possible to use like code syntax to use for ambiguity resolution?
Yes, that's one of the possible. Yes, that's what I meant by context-aware suggestions. So if you use some kind of syntax parser, then there would be less number of possibilities that make sense in terms of the parsing the syntax. So that could limit the number of possibilities that would alleviate difficulty. Yeah, that's
okay. Thank you.
Thank you.
We have a bit of time. I have a question. So you based your approach on operational transform, and I was wondering if you looked at CRDTs, the convergent replicated data types, because I think you may have fewer ambiguities. I'm not sure, but.
So that's a good question. But so we used the operational transformation because of its simplicity. And because we are familiar with the operational transformation technology, but you can use any data representation for the unit of text operations. But even though you use other data representations, essentially this problem still exists, and the possibilities will be the same. I mean, so it's not tightly related to the operational transformation or any other representations.
Okay. Well, thank you very much.